Hello, everybody. So we'll get started because we have to be very strict with time today. Thank you for coming to this workshop. It's a hybrid event, which is a bit unusual for the IMEKO conference because this is a joint event with the CIPM Forum for Metrology and Digitalization and with IMEKO. So because it's a recorded event, because there are people online and it's being recorded, we want the people online to be aware of that, so you will be in a permanent record afterwards. And also we need people to be very careful to use a microphone so that the conversations and things are always audible to everybody. So we must use microphones in the room. If you want to speak, please wait until you have access to a microphone. If you're online, you have an option of raising your hand and drawing attention to people here in the room who will give you an opportunity to speak, or you can type something in the chat. So this is a workshop, and so the purpose is really to stimulate discussions, exchange of ideas on this topic of traceability. So I ask you all to really engage in what we're going to do here today. Some of what you hear may provoke thoughts, and we would like you to share your reaction, share your thoughts on this topic. So, because this is a joint CIPM IMEKO event, I'd like to pass over now to Frank Hartig, who's president of the IMEKO, to say a few words about how it got started.
Yeah, thank you very much. Moin. For those who didn't understand, that is a typical greeting of Hamburg, where we are here in Germany. I think all of the IMEKO participants know it because they hear it every second, but those of you who are online haven't had this possibility. Yeah, I'm really, overwhelmed to see so many competent and prominent people here, and we have as well some super prominent people here. Georgette McDonald, because she is one of the important person at CIPM who chairs or co-chairs or however it's called, the Forum for Metrology, Digital Metrology. So yeah, it's a joint meeting as Mr. Blair told us, and I would like to give as well some information about that. In March this year, so we met at the BIPM, and that was, in my opinion, the really kick-off of this forum. And during this forum, we heard about the mission of the forum. The mission is to advise the CIPM, the highest authority in metrology, more or less, on the SI digital framework in a wider implication of the global digital transformation for metrology and for the international quality infrastructure. So that is exactly how it is written on the BIPM webpage, and that is the spirit. We are going into a new age. We try to transform everything which is, let's say, material, like the artifacts, going in a digital direction and form a digital infrastructure. So many of leading organizations formed a so-called joint statement of signatures. And among them were OIML, CIPM, ICE, and many more, and IMEKO. And that is why IMEKO comes into the role. IMEKO is an organization which has 42 members worldwide distributed, addressing metrology. And in my opinion, it is very important that we, the IMEKO responsible, inform about the activities of the forum, and vice versa, that we get that we bring in information of the metrologies of IMEKO into the discussion which is going on at the CIPM. So that's why we are here, and that's why we raised fingers during this March meeting together with Blair Hall, who spent no effort to come from New Zealand to Germany, half around the world, and the way back one time around the world to give us and to chair this wonderful workshop, joint workshop today. As well, I would like to thank all others who are involved in preparing this workshop. I would like to thank all the speakers who didn't spend their effort to give us a good presentation, to motivate us for discussion and so on. And with that, I would like to thank TC6, TC8 and TC21 from IMEKO, who had strong shares here in the workshop. I wish you all an interesting time, interesting discussion. That is more or less the kickoff of this joint meeting. I hope that it remains for a long time. Thank you very much. Blair, I give the word to you back. Have a nice day. And yeah, thank you very much.
Thank you very much, Frank. So the format for the workshop, there will be two halves, two sessions. We have a coordinator for each session, 4 speakers in each session. The speakers will have allotted to them 20 minutes, maximum 20 minutes. If they use all that up, we go on to the next speaker. If they finish more quickly, there might be time for a question or two. But at the end, once all 4 speakers have finished, then there will be a panel discussion. So all 4 people will be sitting here at the front, and the discussion is open. So the coordinator may seed a few ideas, but we would like you to participate as much as possible in this. So that's how we're going to play it. So the first session chair is Alistair Forbes. Alistair's a fellow in the Data Science Department at the National Physical Laboratory in the United Kingdom, and he's a visiting professor in the Computing and Engineering faculty at the University of Huddersfield in the UK, and in the Mathematics and Computing and Information Science departments at the University of Strathclyde. He's a professor many times over. His research interests are in mathematical and statistical modeling, numerical analysis, and scientific software engineering applied to metrology. He's recently been involved in aspects of digitalization in metrology, such as scientific computation and with dimensioned variables. He was a member of the expert group advising the CIPM task group on the digital SI, and he's the chairman of IMEKO 21 mathematical tools in metrology. So Alistair, you're in charge now for the next.
Thank you very much, Blair. That's a very kind introduction. So as Blair says, we have 4 speakers in this session, the first of which is Charles Elbrich, who was a program leader at the International Metrology Program in the Physical Measurement Laboratory, NIST. And Charles has had a fabulous career interacting with many international bodies. Notably, he's been chairman of the Joint Committee for Guides in Metrology, Working Group 2, responsible for the International Metrology Vocabulary, as well as many other committees. So he's one of the most impactful researchers in our metrology community. It's a very pleasure for me to introduce Charles to give his talk. Thank you.
Thank you very much, Alistair, for that very kind introduction. And I'd also like to thank Blair for inviting me to open this first session with an overview of traceability principles that were first established in the late 20th century, and many of which are still applicable today. As the title implies, I'd like to explore extending the concept of metrological timelines for visualizing metrological traceability into the digitalization world, where a digital calibration certificate might include the timeline of activities necessary to demonstrate traceability of measurement results that are obtained when using the instrument for which the calibration certificate applies. And I'd like to start by looking at the seemingly simple and straightforward concept of metrological traceability and show both the importance of the concept, which I'm sure everyone here appreciates, but also how it can get complicated very quickly. Okay, so beginning with the definition shown here from the latest draft of the International Vocabulary of Metrology, or VIM, metrological traceability is a property of an individual measurement result, which in most cases is taken as a value of what's being measured, along with a statement of uncertainty associated with that value. And so quite simply, metrological traceability provides the documentation demonstrating the connection between an individual measured value and its associated measurement uncertainty to the definition of the measurement unit for the kind of quantity of the measurement unit, such as length or mass. And that connection is provided by the unbroken chain of calibrations of other measuring instruments or systems to the measuring instrument that's being used to provide the measurement result for which traceability is being documented. And while these words define metrological traceability, I find it a lot easier to visualize this using diagrams. There we go. Oh, okay. Okay, so the diagram I show here, which is not a metrological timeline, is probably one that you've all seen in one form or another, showing schematically a path from the International System of Units, or SI at the top left, through a National Metrology Institute and various accredited calibration laboratories to the measurement of a measurand, such as the mass or weight of a product using a grocery store scale, as shown at the bottom right. And while such a diagram can be useful at a high level, it unfortunately does not provide the level of detailed information that's frequently necessary to demonstrate to the discerning metrologist, auditor, or inspector the traceability of a measurement result. And in just a minute, I'll show you a kind of diagram that my NIST colleague Stan Raspberry and I developed in the late 1990s that we called a metrological timeline that provides such detailed information. And that might be useful in digital calibration certificates. But I'd like to first provide a very simple example of the metrological traceability concept to help further set the stage visually. Okay, so thanks. Okay, so let's begin by considering a straightforward measurement scenario where I need to know the length of a table in my calibration laboratory for some reason. I bring out my meter stick, which is marked down to units of millimeters, and I can perform a measurement by directly laying the meter stick lengthwise along the tabletop and viewing and recording the markings that are aligned with either end of the tabletop. And without getting into complications like the uniformity of the length of the table, which to my eye looks relatively uniform, so I perform a few measurements at different locations on the table and obtain an average of 700 millimeters with a spread in the values, in the measured values of 3 millimeters. Okay, so next let me consider the measurement uncertainty to associate with this measured value, which must take into account not only the 3 millimeter spread in the values that I found, but must also take into account how well I believe that the markings on the meter stick are correct, okay? Especially the 1 meter marking from which the centimeter and millimeter markings derive. And this is where the most fundamental aspect of metrological traceability enters the story. How do I know that my measuring instrument, in this case the meter stick, is giving correct values? And in fact, what does it mean that it's giving correct values? Correct values with respect to what? And of course, we typically mean correct with respect to how the measurement unit that we're using is defined and realized, in this case, the meter as defined in the SI. But another key aspect of traceability is measurement uncertainty and the number of significant digits that a measured value can have in a given measurement scenario. And I'll return to this last point a little later. Thanks. Okay, so in order to know whether my meter stick is giving correct values, at least at the 1 meter mark, for many years, I could have in principle taken my meter stick to the BIPM and had them directly compare the 0 and 1 meter marks on the meter stick to the international prototype meter maintained there, as shown in the photograph at the lower right. Now, let me emphasize right from the start, however, that taking or sending anything directly to the BIPM for calibration is exceedingly rare. And so I'm using this example strictly for purposes of conceptual simplicity. And further, whoops, not sure what that's about. Thank you. It's okay. Further, the situation is quite a bit more complicated for several other reasons, including that considerably more modern and sophisticated length measurement instruments exist than in my simple example, but the conceptual principle is frequently still the same. And I'll return to the complication shortly, but let me just point out now that in order to perform the calibration of my meter stick against the International Prototype Meter, there are two physical objects involved, the meter stick and the International Prototype Meter. And they both have the property or quantity length. Next one. So say that I take my meter stick to the BIPM and they compare it to the prototype meter there and find that there is agreement within a small difference that can be characterized and used as a correction when I use the meter stick after I return home. Is that sufficient for me to be able to say that the measurement results when using the meter stick back home to measure my table are metrologically traceable to the International Prototype Meter at the BIPM? And the answer is no, unless I've taken precautions to ensure that my meter stick hasn't undergone any significant changes after it's been compared against the International Prototype Meter at the BIPM. And for those of you who are not metrologists, I'll just add that these are the kinds of things that metrologists like me worry about for a living. And there are, of course, techniques for verifying that nothing significant has changed, as I'll show in the next two slides. Okay, so here I show such a technique using what are usually called control standards or sometimes check standards to monitor the performance of a measuring instrument. The measuring instrument and one or more control standards are periodically used to measure the same stable control artifact shown by the blue rod at the bottom of the figure. And the measurement results are presented in a control chart as shown here at the bottom. The control chart here shows measured values and associated uncertainties of the control artifact using the meter stick and the two control standards at two different points in time. Now, if the times T1 and T2 shown in the control chart down here at the bottom, okay, are respectively measurements of the control artifact made using the meter stick before and after the trip to the BIPM, then it's reasonable to conclude that nothing significant happened to the meter stick during the trip. Next slide. However, if upon return from the BIPM, the control chart looked like this, where the measured value using the meter stick here had shifted at time T2 with respect to the measured values using the control standards, then there would be a need to assess what had happened to the meter stick during the trip. And it would be necessary to use caution when using the meter stick to provide measurement results that were intended to be metrologically traceable. Now, as I alluded earlier, part of the consideration would be the scale of the vertical axis and the number of significant digits that were intended to be used when reporting a traceable measured value and uncertainty. When operating at state-of-the-art levels, this can be an important consideration. And of course, such control charts can also be used to monitor for any other changes, such as drift over time of the meter stick. So this is all to point out that demonstrating metrological traceability goes beyond just documenting that a calibration has taken place, as one of my first diagrams implied, but also includes documenting that systems are in place to ensure that the calibration is still valid when using the measuring instrument to provide traceable measurement results. Next slide. So here I show an example of a metrological timeline illustrating the simple scenario that I just presented, taking my meter stick to the BIPM to be calibrated. Time is shown at the top along the horizontal axis, increasing from left to right. The two levels below the time axis show locations at which various steps take place towards demonstrating traceability, and the boxes and arrows detail the steps taken. In this example, the top level is the BIPM, and the box with the P inside represents the BIPM's primary realization of the definition of the meter, which in the example above is the International Prototype Meter. And the box with the C inside represents the measuring instrument, okay, here, okay, that's ultimately intended to be used to provide traceable measurement results, which in the example above is my meter stick. Now, below the BIPM level is the level where the meter stick's being used to measure something, such as the length of my table, which in the example above would be my calibration laboratory, where my table resided. So let me take you through this timeline step by step, beginning at the earliest time on the timeline T sub B. Next slide, please. One more. Yep, thank you. Okay, so this is a time before I go to Paris, where I measure the control artifact with my meter stick and the two control standards and record the measurement results in a control chart, like I just showed. Okay, next click. Thank you. Okay, then after time T sub B, I then take my meter stick to the BIPM, as shown by the thin sloping dashed green arrow right here. Okay, where at time T sub B IPM, shown up here, okay, my meter stick is calibrated against the International Prototype Meter at the BIPM, recording how much difference there is, if any, between the ends of the International Prototype Meter and the 0 and 1 meter marks on my meter stick. Okay, next click, please. Thank you. And then after returning home, as indicated by the next thin sloping dashed green arrow, at time T sub D, I again measure the control artifact with my meter stick and the two control standards and record the measurement results in the control chart, as I showed earlier, and compare the results to see if anything has changed with my meter stick during the journey. Okay, next clip. Thanks. And if nothing significant has changed, then the next thin sloping dashed green arrow indicates that at a later time, T sub M, I again measured the control artifact with my meter stick and the two control standards and record the measurement results in the same control chart. Okay, if you do 2 clicks, one more. Okay, thank you. If again, nothing significant has changed, then I feel confident using my meter stick to perform a length measurement, such as the length of my table, and can say that the measurement result is traceable to the International Prototype Meter at the BIPM, is shown by the heavy dashed sloping arrow right here. And that points back to the box representing the International Prototype Meter as it existed at the time TBIPM, so when the calibration took place. So for even this very simple calibration scenario of taking my meter stick directly to the BIPM to be calibrated, the precautions needed to be taken and the corresponding metrological timeline shown here are already somewhat complex. Next slide. And of course, this simple scenario is quite unrealistic in the vast majority of cases of calibrating measuring instruments, since, as I said earlier, having a measuring instrument calibrated at the BIPM is rare indeed. Instead, as I showed earlier, there's usually a chain of calibration laboratories between where a measuring instrument is used and the BIPM. And this can result in very complex metrological timelines indeed. Next slide. So here I show a 3-level timeline where a testing laboratory is shown claiming traceability of a measurement result to a measurement standard in a calibration laboratory 2 levels above. Now, I won't go through this scenario in detail, but we'll just mention that each time a new calibration level is added between horizontal dotted lines, a new calibration certificate or report must be provided by that latest calibration laboratory. And each calibration certificate should provide information about the process and steps that were taken in the laboratories above it in order to ensure that the newly calibrated measuring instrument or system is capable of providing measurement results that are metrologically traceable. So one of the things that I'd like to put out for discussion today is whether moving to digital calibration certificates would help facilitate the inclusion of such timelines in demonstrating that the calibrated measuring instrument is capable of providing traceable measurement results as I've described. Next one. Okay, and the last aspect of traceability that I wanted to bring up during this presentation has to do with complications that occur at the top of a traceability chain at the BIPM and National Metrology Institute levels. I believe that much of this traceability workshop will actually be focused on this aspect. And since I'm just about out of time anyway, I'll just briefly introduce the topic and look forward to hearing what other speakers have to say about it. So here I again show schematically taking my meter stick to the BIPM to have it calibrated against the international prototype meter. But then I show below that I can also calibrate my meter stick using properties of nature, in particular well understood and characterized properties of cesium atoms and light. Now, of course, I cannot directly calibrate my meter stick against cesium atoms and light, but I must design and build an instrument or system that allows me to make a physical comparison. As most of you are undoubtedly aware, a few years ago, the definition of the meter, along with the definitions of the units of all the SI-based quantities, were formally changed in the SI brochure in terms of the so-called defining constants, which are constants of nature that are assigned fixed values with no uncertainty. And this is the so-called new SI. Next slide. But the words defining the units in the 9th SI brochure are just that, they're words. Okay. But of course, it's not possible to compare properties of physical objects, such as the markings on my meter stick, to a paper or computer screen with words written on it. Rather, an object must be constructed that corresponds to the written words. And these objects that can be compared to are what are called practical realizations of the definitions of the units. And they can be constructed according to the guidance provided in the so-called mise en pratique in the SI brochure. Now, I don't have time to go into any details about this now, but just show here the sequence of steps at the top of a traceability chain that should be documented in order to provide a complete description of the traceability of a measurement result, excuse me, to the definition of the SI unit. The mise en pratique for the measurement unit is first used to develop a physical realization of the definition, as shown in the middle box in blue. And then the physical realization can then be used to calibrate one or more working standards, as shown in the bottom two boxes. One of the advantages of the new SI is that such realizations and calibrations do not need to originate at the BIPM or even at a National Metrology Institute, but rather anywhere that has the resources and expertise to build such a system, as I indicated in bold in blue in the bottom two boxes here. Okay, so next slide. Thanks. So here I show a possible high-level metrological timeline for the BIPM, where it realizes the definition of the unit by developing primary standards denoted by the box with P in the middle. And again, control standards need to be maintained to track the stability and consistency of P as time goes on, even at the BIPM. Next slide. But as I mentioned, a National Metrology Institute or other high-level laboratory might also realize and maintain such high-level primary standards, again denoted by P. Okay, next slide. And then, as I showed earlier, these standards can be used to calibrate standards denoted C from other laboratories, which can be documented in a metrological timeline such as this, with the National Metrology Institute or other high-level laboratory at the top. So I'm hoping that one of the things that this workshop today will be used for is to explore the feasibility of modeling and digitally incorporating metrological timelines such as this into digital calibration certificates for the demonstration of metrological traceability. Next slide. Okay, so I'll stop here and we'll take any questions if there's time. But either way, I look forward to the other presentations and to the Q&A panel sessions at the end. And for those of you who are interested, I've provided the citation and the QR code to the timelines paper that I've been referring to. And I have a few copies if anyone's interested. So thank you very much.
Thank you very much, Charles. I think in the interest of time, I think we will move on to the next speaker.
Okay.
But we'll have in order to maximize our time for the discussion. So our next speaker is Blair Hall, who's a distinguished scientist at the Measurement Standards Laboratory of New Zealand. And he's a member of the NCSLI, Management Information Infrastructure Committee, as well as members of IMEKO technical committees. And Blair has been one of the champions for raising a profile of metrological traceability within our communities and wider. So thank you very much, Blair, for your hard work in this area and putting this session together. So the floor is yours.
It's working? It is. I like gadgets. I'm a bit worried that this wasn't. Oh, it is working. Oh, good. Okay. Fantastic. Yes. So connecting digital traceability chain together. How am I going to? I'm going to try and take you out of your comfort zone slightly. I want to go beyond the standards, the normative standards, normative reference documents and things that we usually refer to just for a moment. So the GAM, the VIM, 17025, go beyond those a little bit and see what's behind that, what underpins the notion of traceability. Recently, I was reading a book on metrological infrastructure, and it just occurred to me, they said quite nice things, that traceability is a vital element of metrology. We would all agree with that. But I noticed how much they would add adjectives to their discussion: trustworthy, secure, confidence, correct, reliable. They even talked about binding units. I'm not quite sure what they are, but so if you think about when you've been studying your science, your physics, you don't talk about Newton's laws as being trustworthy. You're not bound to the laws of thermodynamics and things like that. So there's something about the way we talk about traceability which incorporates all of the infrastructure required to give quality assurance, and that's very important. But there's also something which is more fundamental, and so I'd like to explore that more fundamental thing today with the time I've got. So my talk, I'm going to try and give you a value proposition for what traceability is, what needs to be traced in order to provide traceability. I'm going to emphasize modeling, which I think is fundamental. I think without a model, we can't claim traceability. And I'll try and explain how I think we link the traceability chain together. So traceability provides objective information about the physical world. That was going to fall over whatever the calibration certificate said, right? The world works, and we model the world through our understanding of physics. And if we don't get accurate information about material things, then we can't make good predictions. So accuracy matters. And in my opinion, the value of traceability, the real value, is only at the end of the chain, where some decision has to be made based on information about the real world that you obtain through measurement. So the steps leading up to that are all helping to make that decision, but the value is at the end. So it's decision making, which society relies on. We want to trust. There's that word again. We want to trust in various things in society. Planes fly, and electricity flows in the wires. And this involves comparisons. This involves comparing one thing with another. So back in New Zealand, we kind of put together a statement that we thought would capture traceability. in quite a different way from the sort of the VIM definition. So for quantities to be meaningfully compared, they must be expressed on a metrologically traceable measurement scale. So that's what we came up with. So this says that this really expresses traceability rigorously relates measurement results to reference standards. That's embodied in there. It supports exchange and use of information obtained using different measurement systems. And it's essential to form critical decisions. When decisions matter, we want to use traceable measurements. But further to that, it ensures accurate and reliable information is obtained by measurement in various fields of science, chemistry, physics, engineering. So that supports fundamental scientific goals of reproducibility and verification. So perhaps this is actually a scientific principle. I had an argument with ChatGPT about that, and it agreed with me after I explained it to him. So decisions. Traceable measurement produces really two things: a numeric value, which is an estimate of what we want to know, and we know that that value is in error to some extent. So here on the right, got the idea of somebody measuring a speed of a vehicle and deciding whether or not to issue an infringement notice. So we don't want to think that our speed control is unfair. And so there are good outcomes, there are fair outcomes. Speeding driver should be issued with an infringement notice. A driver who's driving safely should not. But it is possible, because of measurement error, that you would incorrectly issue infringement notices. So there are good outcomes and bad outcomes. If we know we don't know the value of the measurement error, but if we know the probability that error occurs, the nature of the of the error, then we can design decision-making processes, like the little boxes there, which are fit for purpose, which we will satisfy our needs. So, how do we capture the traceability? How do we capture this idea of measurement values and measurement errors and so forth? We need a model. We need a model that somehow explains the accuracy of the data that the measurement is producing. So these are a few slides to show you a notation that we've developed at MSL so that we can write these things down. So here on the right, we have measurement system. Our measurand, the thing we would like to measure, is capital Y. What we've got is little y, an estimate of that. And in fact, come back, we have an error, dy. Now we know the value of little y. We don't know the value of capital Y or EY. So unknown quantities, we give them capital letters. Known quantities, we give them lowercase letters. And when we would estimate the value of a quantity as 0, we write a capital E and then a little subscript. So that is the model that all of you who have issued a calibration certificate have used. That is saying that the measurement, the quantity I intended to measure is equal to the quantity I'm telling you in the calibration report, plus an amount of error that I didn't know. You didn't know it, but you might have issued an uncertainty statement because you know probabilistically about how that behaves. That's the work of metrology institutes, to understand and characterize their experiments very carefully. Now, is measurement just what you do in your laboratory? Or is measurement everything that happens, and Chuck showed a chain of, a bit like this as well, until you get to the point where somebody's going to use that measurement result? And I think it's the latter. And so this diagram is intended to sort of say there are stages, a couple of stages up here: primary laboratory, secondary laboratory, and then some sort of use. And the red dotted lines are where we report between stages. Now, I'm sorry, this isn't a very nice slide, but I'll take you through it as best I can. This is just part of a traceability chain related to the idea of a very simple weighing device, balance. And so at one step here at the top of the chain, we have some sort of, I'm not a good driver of the red dot. We have a reference weight. We're going to use this reference weight to characterize a bias in the instrument. And so all we know about the reference rate is the value that we get from its calibration certificate, but we can model it in this way. When we then have a procedure to correct for the bias, we're estimating this quantity A, we will get a value little a, and there'll be an error associated with that, but we can then have a model of what's going on here, which is more detailed. We use the balance to weigh something else, and then we have to incorporate our offset correction, which incorporates information about the reference standard that was used to calibrate the balance and so on. So here in all its glory, if you wanted to, you could identify every term that contributed to the outcome of a particular measurement. You could identify them all if you wanted to. And that is what I'm thinking of in terms of modeling. And so the whole measurement model is composed of these submodels that were shown on the earlier screen. It's composed in the sort of mathematical sense. The overall measurement model is this sort of thing, where one result feeds into another. Now, to evaluate the model, it's easy if you have the value here and the value here, and you want to know the value here, it's easy just to pass the values along. You don't need any more information. You could report the value in a certificate, take that value, do it for what you want to, and on and on. But if you want to report, here we go. If you want to report an uncertainty that would be GUM compliant, the LPU in the good old GUM, you're going to need here at each reporting line, you're going to need to report information on all the components of uncertainty. If you don't do that, and we don't at the moment, then you're throttling off your model. You're not evaluating the whole model. Now, let me give you an example of why that's not a particularly good idea. Very simple example. Light meter. My colleagues tell me that when light meters are calibrated, there's a dominant effect, which is due to the calibration itself, and is therefore systematic afterwards in the use of that meter. So we have a simple model here that the light level is equal to the light level that's registered by the instrument. And then there's the systematic calibration error and a little bit of random error for each measurement. Random error is about 1/10 of the systematic error. But if we're going to survey the light level in an industrial space or something like that, we're not interested in the light level, we're interested in the light level difference between different points in the room. And so if we evaluated the measurement model in that case, these terms, this term here would be very, very small. So it attenuates the effect of the fixed calibration error. And so if you know about the details that pass along through these lines, you don't summarize them to one number, then you can give much more nuanced information at the end user. So you can make better and more accurate measurements and better decisions. We don't do this at the moment, but a talk later in this session will show just how powerful this idea is. So to summarize, metrological traceability, I hope you agree with me, is a scientific principle. It's one of these underpinning things. It's supported by documentary evidence from our quality assurance system. So the two things work together. Value of traceability is that it enables critical decision making. Traceable measurements are actually staged, and we should look at the whole picture. We should have a model of the whole picture. It's indispensable because it's those terms in the model that we are tracing through. trying to see how they influence the final outcome. Links between stages provide this information, so we need the whole model. And modeling can be supported by digital technologies, and this will be shown in a talk from somebody shortly. So thank you very much.
Thank you, Blair. You're under your time allotment, so
I went over my time.
did you? No, you went under.
Under? Oh, okay.
Yeah,
Well, then
so-
we could have some questions.
Is that what you want to do?
We were a bit behind because of the lead-in, so maybe we just,
Yeah, I think, yeah, I want to maximize the time for the general discussion, I think. Thanks very much, Blair. Now, our third speaker, because we are now in 2024, we can do things differently. So our third speaker is Ryan White. He's from the lead for the digital metrology at the National Research Council in Canada. And he's worked as a delegate to the CIPM forum in metrology and digitalization. I think he's newer to the metrology domain, but he's having a significant impact already. I know him from his work on the expert group, advising the task group on SI digitalization, and I know he's been very impactful and already doing very, very interesting things. So we're going to have a recorded presentation from Ryan. My colleague is going to start it up now. Thank you.
Hello, my name is Ryan White. I am a research officer at the National Research Council Canada. I would like to thank Blair Hall for organizing this workshop on metrological traceability at the IMEKO World Congress, and to thank him for inviting me today to share with you this idea of provenance in the context of metrological traceability. I apologize that I cannot be there in person. I hope this talk engages the audience and helps to have a interesting panel discussion at this workshop. So in this talk, I want to motivate the idea that provenance and metrological traceability are properties of a measurement result. And so we will discuss what provenance and provenance metadata are. And I will introduce a very simple conceptual model for metrological traceability that I hope will be further discussed by other speakers and members of the panel. And really the focus of this talk is to discuss why it's important to distinguish these concepts so that we can improve upon current practice. Now, provenance, if we look at the formal definition from the Oxford English Dictionary, is the fact of coming from some particular source or quarter. It's regarding a source or derivation of a source. And provenance is initially applied to works of art or historical objects, as they are to establish authenticity and trustworthiness of the origins of a piece of art or the historical object. What I show here is a very famous example from the J. Paul Getty Museum of a Kuro statue. It's a multi-million-dollar statue, which was later discovered that the aging of the stone could be done artificially, and therefore having some record of its provenance would help prevent such works of art from being simulated. But provenance has been growing in terms of a concept that's used around data and information. For instance, there's database provenance. It's characterizing and computing the provenance of a query result. So this is capturing information about how and why certain data items has become part of a query result. There is also process provenance. These are the data dependencies that account for the generation of a piece of data as a result of a sequence of process transformations. Process provenance is of increasing interest in scientific and fair data so that we can understand where the data came from. This is also sometimes referred to as data lineage. However, provenance could really be thought of as a domain agnostic concept. We've already seen that it's initially applied to art and historical objects, but later in terms of data and information. So really provenance is just a general concept about information about entities, activities, people, and institutions involved in producing, influencing, or delivering a piece of data or thing, which can be used to form assessments about its quality, reliability, or trustworthiness. This is a definition from the W3C working group on provenance. But now, if we look into the literature, there's really no universally accepted definition. It's best to define provenance in its appropriate context. So really, it's necessary to know what the information is to be used for. So already we can start to think about how provenance relates to a measurement result. It's generally very important to understand what a measurement result is to be used for. And so provenance may play a role in helping to establish this information. The W3C working group set out to define the required content for provenance. So first of all, there is the object. This is the artifact the provenance statement is about. So if we want to relate these to metrology, this could simply be about the measurement result itself. There is attribution, so description of the sources or entities contributing to the artifact. Again, in the case of metrology, there's authorized staff, there are the measurement systems, reference standards, laboratories involved. There's description of process. These are the activities or steps to generate the artifact. So we could simply say there's a calibration, but there may be more details, such as the measurement methods used in a calibration or measurement activity. There's justification. So there's documentation of decisions as part of a provenance content. In our case, this could simply be the authorization of measurement reports or calibration reports. There is also entailment, so the explanations of derivations of facts. And so this we might think of in terms of supporting documents for uncertainty statements. And so now I'd like to turn some attention to metrological traceability, so that we begin to differentiate between provenance and traceability as properties of a measurement result. So the definition from the vocabulary of metrology that we're familiar with is a property of a measurement result whereby the result can be relayed to a reference through a documented, unbroken chain of calibrations, each contributing to measurement uncertainty. I think it's important to point out that the value of metrological traceability is its assurance and quantification of measurement accuracy, through which the role of the national measurement standards is realized. Here we see that metrological traceability is distinct from provenance, in particular, this quantification of measurement accuracy. So from this definition, we can think of a very simple conceptual model of traceable measurement, in particular what our current practice is. So traceable measurement can be considered as a series of stages, each contributing to a final outcome of a measurement. At each stage, there is a demonstration of competence in calibration, whereby it's demonstrated that influence quantities that contribute to a measurement can be accounted for in terms of the error on a final measurement. Then at each stage, there's the documented likelihood of error on the final outcome. This information is passed along to the subsequent stage until all this information is accounted for in a final stage in a traceable measurement chain. Now, if we wanted to just extend a bit our current practice of establishing quality of traceable measurement. In addition to documenting the likelihood of error and final outcome at each stage, we can generate a provenance record of the measurement result at each stage. These two demonstrate an unbroken chain of records that are associated with a traceable measurement. Now, I laid out this simple conceptual model so that we can then answer the question, how do we assess quality of measurement? Now, there is the competence and calibration. There's the quantification, measurement accuracy, and there's the provenance of a measurement result. The information about the activities, agents, and entities involved in generating a measurement result. So let's look at provenance and metrological traceability as properties of a measurement result. So provenance focuses on data's origin and history, or a thing's origin and history. This involves entities, agents, and activities. As I've shown, it's really a domain agnostic concept. And in terms of data, it can be used to assess data quality. Metrological traceability, on the other hand, is focused on measurement accuracy. Provides information related to the measurement results, measurement standards, and it's specific to metrology. And it's there to document the likelihood of error. Now, in both cases, provenance and metrological traceability are documentation associated with the measurement result. They're both there to establish for quality assurance that can establish integrity of measurement results, as well as the trustworthiness of those results. So now to start thinking about how we can improve on current practice, let's look in more detail of the provenance data model that the W3C working group has established. The data model includes entities. These are real-world, informational, or even conceptual. So in our case, these could be a measurement result, or something more conceptual, such as a measurand. There's activities. These are the processes generating or changing entities. Or, for example, a calibration activity. There are agents. And these are the people, organizations responsible for activities, such as a calibration lab. Then there are roles. These are functions entities play in activities. So, for instance, there may be a role of vindicating qualified technical staff authorized to carry out particular calibration activity. There are plans, which are a type of entity. These are predefined procedures followed in activities. So, for instance, these could be the document measurement methods. There's also time. So it's a recording of timing of significant events in a provenance record, which of course is an important detail in a calibration or measurement report. So this data model is fairly simple. As I pointed out, there are the description of entities, which are generated through activities. Activities can be associated with agents, and entities can be attributed to agents. Entities could have relationships, as well as activities having relations, and there may be relationships between agents. This is the formal W3C data model on provenance. So let's just try to understand how this data model works. We can simply look at an example of a file generated from editing the original source document. So in this case, we have entity 2. It is a file That's generated by a provenance activity, in this case, an edit activity. This activity used the original or primary source, provenance entity 1, whereby provenance entity 2 was derived from entity 1, and entity 2 was attributed to a agent, in this case, a person. So that is a very simple example. And so now let's consider how provenance and the provenance data model can be used to establish measurement quality from a provenance record. Well, we can just pose a few simple questions. Does the organization have the capability to perform the activity? Who is the agent qualified to perform the activity? Who is the authorizing agent? What is the measurement method used? What is the measurement system that generated the measurement result? These simple questions can all be answered with information about the entities, activities, and people involved in producing a measurement result. And this information can be used to form assessments about its quality, reliability, or trustworthiness. So again, we can take the provenance data model and create a very simple example of how a measurement result is generated from calibration activity and how we could document this in terms of the provenance data model. So in our case, the entity in question is a measurement result. It was generated by a calibration activity. This activity used a plan, which is a document calibration method. The activity used a reference standard, another entity in the provenance data model. And here we may have additional semantics, describe how the measurement result is traceable to a particular reference, another entity. The calibration activity was associated with a particular agent. This may point to a particular person at a particular lab. Okay, well, I think really now that we understand provenance is distinct from metrological traceability, and that there is this existing data model, and we need to ask, what would be the benefits of adopting this existing provenance data standard? Well, one, it does allow the metrology community to rethink current modeling approaches, because it would allow us to clearly define concepts in a measurement or calibration report. And once those concepts are clearly defined, we now have a structure with a well-defined set of semantics to express provenance of metrological traceable measurement results. In addition, the adoption of an existing data standard starts to de-risk dependence on our internal approaches for concepts that are not particular to metrology. By doing so, it allows us to reuse existing technology that may be developed based on a data standard. Thereby, there could be established solutions for provenance record management, as well as security and confidentiality solutions, which can mitigate our stakeholder concerns in our path towards digitalization. Moreover, this is a step that we can take for establishing best practices for implementing fair data for metrology, findable, accessible, interoperable, and reusable data for metrological purposes. I think what may be a little bit more important, though, is that by investigating how we can best use provenance as it applies to measurement results and traceable measurement, we can develop a set of best practices for implementing metrology-specific information for data, for fair data. So in summary, the clear separation of concepts and metadata in digital format does improve the clarity of the information, interoperability, quality, and trustworthiness. as well as machine actionability. These are all very important if we want to digitalize measurement results. Now, the provenance data model does allow us to incorporate metrological specific details without making changes to the underlying data model. We can incorporate the DCC namespace, for instance, digital calibration certificate. We can adopt standardized taxonomies for describing various aspects of the provenance data model, such as entities. There may be other formalized digital document standards that we can incorporate as well. These may be digital calibration and measurement capabilities, or digital scopes of accreditation, possibly digital certificates of reference materials. So to conclude, I hope I've motivated this idea that provenance and metrological traceability are distinct yet complementary concepts that are both properties of measurement results, and they are both essential for the integrity of a measurement result. And that by modeling concepts appropriately, this will lead to machine actionability for digitalization metrology, and that we can tailor existing provenance data standards to meet our metrology specific requirements. I'd like to thank you for your attention. Here is my email. I hope that this presentation contributes to the overall outcomes of today's workshop. I wish you all the best in today's session. And I would just leave you with a few of the references that were used for this work. Thank you.
Yes, for the record, we should thank Ryan's contribution. So let us move on to our last speaker in the session, who is Marco Zayer, who is the head of the RF and Microwave Laboratory at METAS, which is the Federal Institute of Metrology in Switzerland, Switzerland's National Metrology Institute. So his laboratory is known for the state-of-the-art realization and dissemination of SI traceability of high-frequency impedance parameters. And so he's at the sharp end of this metrological traceability side of things. And Marco, you're going to present remotely. So that's news to me, because I was looking in the audience to see if I could find you, and I realized that I couldn't. Marco, the floor is yours.
Okay, first you need to make me presenter. You know, I can't share unless you make me presenter. Okay, well, first of all, I would like to thank to Blair and the organizer for the opportunity to present here. And my talk is maybe a bit more specific than what we heard before, but I listened to all the other three presentations. They were very interesting. And I think I will be actually able to touch on some of the things that were mentioned before. So this is about a metrology software, which is called VNA Tools. And I believe that, you know, I'm able, or I hope that I will be able to show that it is supporting this digital traceability chain already quite well. So this is the outline, and I guess most of the people in the audience are not really familiar with VNA or RF microwave metrology, so I guess I should give a short introduction what this is all about, and then I will give some details about the software and how we think that it actually supports the traceability chain. So let me start with what a VNA is. It's actually just the acronym for a vector network analyzer. It's a very fundamental RF microwave measurement device which measures reflection and transmission. So these are fundamental quantities in RF microwave metrology. It exists in different form factors and for various transmission media, coaxial, on-wafer, and so on. And the working principle is shown on the right side. It's, you know, the basic I mean, the basic principle is very simple. It consists of sources, of receivers, and on some mechanism to do signal separation. Now, the measurements which are being measured, you know, these reflection and transmission, they're also called scattering parameters. And on this slide, you know, there's a bit of a summary on what scattering parameters are and what the properties are of scattering parameters. I don't want to go into detail here. I think the important part is that these are two-dimensional quantities. So, you know, you measure reflection and transmission by amplitude and phase, but you can also represent it as a complex valued quantity. And usually we use, you know, the type of vector and matrix calculation, which is shown up here to do the calculations. Now, the VNAs can't just be used and, you know, for measurements. They actually have unavoidable systematic errors and they require calibration. So the typical measurement sequence is that you measure a set of known characterized standards. Then you have an error model in which you can determine the error coefficients based on these first measurements. Then you measure the device on the test. And at the end, you use again the error model to correct the measurement of the device on the test. There are different calibration algorithms, you know, they're applied depending on calibration standards, transmission media, device on the test, and so on. So there's a multi-step measurement process. The traceability in these measurements is established through the standards which are used to calibrate the VNA. At, you know, the very fundamental level, these are calculable standards. So, you know, they can be measured mechanically and in combination with electrical measurements, some modeling and optimization process, you can actually come up with SI traceably characterized calibration standards. And then, you know, the traceability chain, as it is shown on the right, is basically established by propagating this from one set of standards to the next set of standards by using the VNAs, you know, to do that. So VNA uncertainty evaluation is rather challenging, and I basically already mentioned it, but I'm summarizing the reasons for it here again. So first of all, the measurements, they are multidimensional. So correlations are really important. So you have to apply multivariate methods. Then there's this multi-step measurement process with calibration and error correction. Then, you know, there's many additional contributions due to coming from the VNA, but also each cable movement, each reconnection basically creates a measurement error, which somehow needs to be accounted for. So the measurement model is definitely not simple. And then finally, these measurements, they are uncertainty, their associated uncertainties are frequency dependent. So it's quite usual to measure several hundred frequency points, and you know, at least for metrology, this is already a relatively large amount of data which needs to be processed. So I think it's quite obvious that for these, this type of, you know, for the uncertainty evaluation, really you need some type of software. And this is now where VNA Tools comes into the game. It's a software which has been developed at Metas. And it basically, you know, it basically uses the raw VNA values and does all the calibration and error correction steps, and it also calculates and visualizes VNA measurement uncertainties. I'm listing the core features on the right side, and I would like to go a bit, you know, I don't want to go through them, but I would like to go a bit more into detail on those with which are highlighted in yellow, because I think they are actually essential for supporting the digital traceability chain. So let me start with the measurement journal. So part of the software is a measurement journal, which really records each measurement step. So, you know, you have the measurement setup, what the device settings are every measurement is being recorded, every cable movement, every connections, the user can make notes and so on. And the purpose of this is basically twofold. You know, first of all, it's a reporting tool. It supports good practice and also quality assurance, because you will always be able to see later what you have actually done during a measurement. And then it also provides the inputs for the uncertainty evaluation. Then some words on how we deal with uncertainties and correlations. So on the very left side, I'm actually showing here, you know, the basic model. So you have the input quantities and you have the results down here. They are, you know, termed as X and Y, and then you have the measurement model in between. And the way we handle it in our software is, you know, each quantity here and also those in between are basically uncertainty objects. And these uncertainty objects, the content of these uncertainty objects is first of all the estimate, the value. And then there's the, you know, what it depends on. So these are the X's here. And the sensitivities with respect to these fundamental input quantities. So it's important to note here that we are not storing in these uncertainty objects any uncertainties, correlations. We just store the dependencies and the sensitivities, and together with the uncertainties of the fundamental input quantities, we are basically able to calculate all these things, including an uncertainty budget, on demand. So that's a really important aspect. So the question now is, how do we keep track of these sensitivities by going through the measurement model? And here comes a technique into play, which is called automatic or algorithmic differentiation. And actually credits go here to Blair Hall also, who's organizing that workshop, because at least to my knowledge, he was the one who brought this concept into metrology and to uncertainty evaluation in metrology. And the way it works is basically, you know, it's basically a linear uncertainty propagation, which is here realized. And you only need to program the derivatives of the elementary functions. And then by going through the measurement model, you just apply the chain rule to create and update the sensitivity coefficients here in the uncertainty objects. If you want more details about this and to understand it better, then I can refer you to the papers Blair published already a while ago. Now, just one word about the importance of correlations. Because VNA tools actually preserves, I would say, correlations to the maximum possibility. Even if you, let's say, have independent calibrations, you know, provided by Metas in this case, you know, so you have two calibration certificates, you will still maintain, or VNA tools data files still maintain the correlation between these independent calibrations. And a calibration lab which uses maybe, you know, calibration standards which they had calibrated at the NMI together in a calibration will still be able to take these correlations into account. And the effect, you know, I'm just showing here an example of a device under test on the right side, where you have the uncertainties in red when you take the correlations into account between different standards, and in black when you don't. The effect can be quite significant. So, you know, here in this example, it's maybe up to 30%, but, you know, there are other examples where it can be even more. Now, a word about data format. So these uncertainty objects, they have to be stored somehow, and you know, we were not able to find an appropriate data format for those, so we had to develop them ourselves, and we basically made two versions. At least, you know, there's actually more versions, but there's two versions which really allow you to store the full information. And so this is in XML and in binary. And you know, what this allows you is actually a full recovery of the entire information when you reload the data files. And then, you know, as I said, you don't have any uncertainties in here in these data files. You don't have any correlations, but you can always get the uncertainties on demand and the correlations on demand, and you can even get the uncertainty budget on demand. Now, if you go to the certificate, in our case, we have digitally signed electronic certificates to which we can attach data files. And the user then basically has the possibility to use the certificate data based on his needs. You know, there was often a question in the past, what, you know, if we have correlations, how should we put them into the certificate? To what extent should we put them into the certificate? This problem is basically solved here, you know, because the user can decide what he wants. He can decide on the format, he can get the uncertainties if he wants, he can get all the correlations he wants, and he can even get the uncertainty budget. And then we also try to support that beyond the certificates. So there is basically, you know, there are tools for further processing, and there is different possibilities here. So we have a reduced form of VNA tools, which we call the Data Explorer, which, you know, you can just use for display, conversion, and export of data. But then you can also use VNA tools itself if you want to do more systematic investigation, maybe for your own calibration services. And on a side note, we have like PDF A3 certificates with embedded data, and they can basically, the certificate can get directly be loaded into the software, and then the data is being displayed. And then finally, there are also commercial solutions by now for the, you know, which are more simplified, automated software to do maybe your own cal services or your own measurements. And 2 of them are available on the market. They both have VNA tools inside. As I said, it's more simplified, it's more automated, it gives more guidance. And one of them is actually running on a VNA itself, so you can have real-time measurement uncertainties on the VNA, and the other one is a standalone service, which is basically device independent, which, yeah. So that this is another option, or, you know, this is another type of support for the end user if he needs to process further. So I hope that, you know, with this, I was somehow able to show that this software supports the digital traceability chain already quite well. And I would like to summarize that a bit here. With the data format, as we define it, you know, we can basically preserve the dependencies along the entire traceability chain. So, for example, the influence of a mechanical reference block here at the top level, because the end user basically, he can, if he wants, you know, he basically can have this to show up in his uncertainty budget. So basically the uncertainty budget is propagated down the entire traceability chain and updated at each step. Now, okay, there might be some limiting factors. Obviously, the further down you go here, the traceability chain, the larger the files get, you know, and this might also influence your calculation speed. But there's an option here that you can actually cut the dependencies at desired levels and transform that into correlations. And you don't lose the correlations which come from the previous level. So, you know, this is very flexible. And, you know, can be, so the data can be transformed based on need, and, you know, sometimes you also have some limiting factors. So I think in this way, you know, VNA tools supports quite well the seamless process in terms of, you know, metrological data down the traceability chain. Now, just to emphasize it a bit, what the usefulness at the end of the chain is. So in a way, it's a bit of a repetition what I already said before, but I think Blair touched on that, end users, they have very different needs. Maybe they just want to stamp on the certificate. Maybe they need to make decisions, maybe they need to process the data somehow further. And so what we try to do is to support the large spectrum of needs and competence level. So the certificate data can now be used, either with commercial solutions, so where you have a largely automated, simplified and guided process that doesn't require a high skill level. You can go a bit deeper with the VNA Tools Data Explorer to visualize, study, and compare data. You can convert and store it in a desired format. For example, if you want to use it in your own software system, or you can go even deeper, and use VNA tools again to process it further, to diagnose problems. So you can study correlations, you can study the uncertainty contributions, the uncertainty budgets, and so on. And you can do systematic investigations. It's, depending on what you need and how deep you want to go. With that, I come to my final slide, where I try to summarize a bit and also a little bit of outlook. So I hope that I was able to show that VNA 2 supports good metrological practice and also is a development towards a digital traceability chain, and also supports the integrity of the traceability chain. The key ingredients to that is to use these uncertainty objects based on dependencies, that the uncertainty budget is therefore being propagated all the way down the traceability chain. Another key ingredient is also that we try to support the customer beyond the certificate. We don't just leave him alone with the certificate. And then there's this flexibility and customizability based on need. As a possible future, and data provenance, data lineage was mentioned before, so it is conceivable that one could even add the measurement journal to the certificate, or maybe even adding measurement models to the certificate. Now the question here, and that's maybe a point of discussion, to what extent would that make sense, or what else would it make sense to add to a certificate to actually arrive at a data provenance which is also useful for the customer or the end user. And finally here, this is the web page. You can find more information about the tool. And with this, I would like to finish and thank you for your attention.
So now we move to the discussion part of the session. So I invite the speakers, Charles, Blair, and also Jeanette McDonald, who's going to sit in for Ryan White. And Marco, you're still with us?
Yes.
Brilliant. I think we're ready. Thank you very much. So if MD from the floor here has a point they want to make, please come to the... Okay, just state your name and can you move that?
Let's try this.
Perfect.
Hi, Henrike Fleischak from PTB. This is, actually for the first 3 talks. I was really impressed by the 3 concepts, and there seems to be a lot of overlap between the provenance, the calibration model, let's say, or the measurement model, and also the timeline that was shown. And I'm curious of what do you think, should we as a community try to come up with like a unified data model where we can combine information about the numerical measurements as well as, say, information about who did the measurement, in the same in the same kind of data model, or if you see this more as being provided as completely separate models where maybe some information is going to be duplicated then.
Thank you. Charles?
Yeah, I'll start. Thank you for the question. I guess from my perspective, it would be useful if all of the information could be combined and people could use what portions of the digital certificate they were useful to them. I think that I don't know how complicated that would be. To me, part of the beauty of the digital certificate is then you don't have 100 pages of paper to wade through, and you can, easily go and look for what it is that you need from the certificate. But I would hope that that the different pieces of information could be harmonized or combined somehow in a certificate, as has been discussed in some of the other sessions. It's not clear who's going to take responsibility for doing this, but I guess that I think having some harmonization would be useful. Thank you.
Yeah, I don't think we should duplicate information. I think that was part of what you were talking about, but hopefully the idea came across that there's traceability, there's provenance, there are these different aspects, and what we need to do is show the relationships between things. So, for example, where I was talking about the measurement model, and I had terms for each thing that was going to influence the outcome of the measurement process. In the provenance model, you could have identifiers for those terms that are then associated with provenance. So Ryan talked about documentation to about the variability of some terms and things like that. So you can link those things together. So the linkages would be duplicated, but the information perhaps not. So that's kind of the way I see things going.
So I'm going to comment that I am a poor substitute for having Ryan in the room, and I apologize for that in advance. But as Frank mentioned when he was doing the introduction, I am also on the CIPM forum for metrology and digitalization, and I think the conversation around where does this end up residing and who takes responsibility for it, that's one of the things that we're trying to understand. Where is the role of the international community in coming together on these things and storing it and sharing it and providing a forum for that? And I think that we need to understand what pieces of it reside with the national labs, what pieces of it reside in an international sort of database and those kinds of things. But how we share the information is as important as what information we're capturing and what it looks like. So I think that there is a place for that discussion. And one of the reasons why it's important that we come together in multiple different so the joint signatories need to have a conversation about how that applies to all of our different organizations. And then the metrology community needs to talk about where does that reside communally. And so I think that that's part of the discussion as well.
Any other response from the floor to those?
Yeah,
Marco, did you want to comment?
Yeah, okay, I can also say something. Well, I think to have like a unified data model, or how did you call it? Yeah, I think you call it like that. Then I'm a bit skeptical to approach that with, let's say, some type of big project and then come up with something which maybe nobody needs, So I think it has to be more of an evolutionary process. So I think it's good to have these forums and people who think about it, how it could look like. But I still think we also have to, or we definitely have to take somehow the needs into account. And because if something is being produced which nobody needs, then it doesn't make much sense. So,
of course, there's a thing you don't know you need it until you don't have it. So from my point of view, one issue that I'm quite interested in, how comprehensive do we have to document this unbroken chain? For instance, training. and competencies of the laboratories that are undertaking these? Have we got traceability if the person using that instrument wasn't trained properly to use that instrument, and how would we know that was the case? So, anybody want to think about that for me, please?
Thanks. So I, having started my career in a calibration laboratory and advanced into sort of doing the assessment of calibration laboratories using quality systems. Sorry.
Just was asking if Alistair wants to be seen as well.
Oh, now I see you have to get seen.
Also, sorry for.
No, it's fine. I think that question about how much we retain and how much we trust sort of other players in the infrastructure to do their role. So if laboratories are implementing quality systems and they have demonstrated that they're keeping those records and they have an accreditation or some other outside source who's giving them the validity, like, do we need all access? Like, do we need to do it all ourselves? Or do we need to understand that the whole infrastructure works together and that we build trust in the other pieces? And so training is something that a laboratory is going to demonstrate through their own records, and they're going to maintain that. And someone is going to evaluate that if that's an accredited laboratory, or if if they're not accredited, but they're implementing a system and you can evaluate, like, that's the process. And we need to build the system all together because we can't keep all the information in one place, but we need to understand what we're trusting and who we're trusting to do those other pieces of it for us.
Good. Charles?
Thanks. So to this point, but also to the earlier question too, kind of seem as being related. What I've always seen as an advantage of the timelines approach is you can you can document what's happened at each step of the way, and then the next lab that's doing a calibration, they've already got all the information in the earlier part of the timeline, and so it's maybe not so difficult to keep track of all of this if that just kind of tracks along in the timeline. I mean, and including all of this information about training. I mean, there's a lot of other information that I didn't include there, that could be included in a timeline of information. I think we need to talk to the accreditation community about this, as far as, just how much information they would need to, when they go out and do audits now. Is what they have enough with digital certificates coming along? Are they going to be asking for more? Do they need more? So I guess to me, that's an important part of the puzzle.
And I'd just like to comment a little bit further. So once again, we've turned our attention into the quality assurance perspective, turning our attention more to the scientific perspective. Sometimes people just want to use the result, right? So a little bit like Georgette, I think, was saying, if the appropriate checks and balances are there, you don't want to open it up and recheck those things. You just want to use the result. And so that little statement that I showed you about metrological traceability, allowing you to compare results, is really the value. And something like the software that Metis have allows you to just use the result. And in the background, the traceability chain is following you. It's stalking you. All of these details about the timeline, everything that's contributed to the outcome is somehow being incorporated in the new result. And so in the example of the light meter, you got correlation was suitably corrected. So there are these two aspects. There's making sure that all the quality assurance is there, and that's very important. But there's this huge advantage that you can just use the result, and this traceability chain is constructed automatically for you.
Okay, I think we can move on to the next point.
Thank you. My name is Daniel Hutschenreuter from PDB. Thanks for the excellent talks. I really enjoyed the session, and I think it was well orchestrated, the topics. So a lot of things you explained are set out well, like the timelines and processes for traceability, the mathematical models and procedures, as well as we see there are communities who already have implementations of great tools. I was wondering what's the stepping stone in realizing this, because when we look at industry standards, ISO 17000 series, 17025, like provenance data and all the requirements are set out. So what's holding us back from making the first step to implement these things digitally? And the colleague behind me, I think, has a similar question, or addition to the question, maybe this could be answered together.
It goes in a different direction. So
Okay. Who wants to respond to that?
I don't know what's stopping us. What, let's get on with it.
So one question I always have is, the metrology community, we in the NMIs, let's put it that way, we spend all our time trying to milk this last uncertainty, reduce uncertainty by 0.1% or whatever like that, and then write a paper. We've got enough on our plate. We have to understand the whole of physics. We have to understand the whole of mathematics. And now we have to understand the whole of computer science and knowledge reasoning. Have we the resources within the NMIs to really do a good job? As Ryan was saying, we should be using the people who have been working in data provenance, the computer scientists, to help us, but how do we get that collaboration going? And how do we fund that collaboration? Because the funding bodies will say, okay, another percentage in their, the uncertainty budget, or spend a whole pile of money on software engineers. Who's going to make that decision and make the right decision? That's my take on some of that. Right. Any other comment?
I don't know. I mean, I don't know, Jim, do you want to say anything to that? I mean, as far as, as far as what's holding it back, I mean, I think this is just new. I think from my perspective, everybody's saying, what is this digitalization all about? What is, really going on? And maybe, I know PTB's taken quite a lead on this, and so there are answers there. But so it's not being held back in PTB. So I don't know if your question is it being held back in other places, or maybe I'm not quite sure what. Yeah, right, exactly.
So I was not asking for PTB, but so general as the metrology communities. So we are discussing these things. We are evaluating what's needed in the future. So in that respect.
Thank you, Dan.
So at the conference, I've been talking to lots of people, and I think one of the things that's holding us back, or holding smaller labs back perhaps, is that our customers don't want this. And where's the need? There's no pull. And so there's a saying attributed to Henry Ford, but perhaps he didn't say it. If he'd asked his customers what they wanted, they would have said faster horses, right? Henry Ford. So they wouldn't have said a motor car, wheeled vehicle for it. And it's a little bit like that. I don't think people quite know what the DCC or the digitalization is. But also, it seems to me that we don't quite know how best to offer value through digital services to our customers. We haven't got that right either. Otherwise, we would have persuaded them by now that they can use it. So that's my opinion anyway.
And so building a little bit on that, I think definitely the non-existence of market pull is a problem for a lot of institutions, that and not clearly being able yet to articulate to ourselves how our institution is going to benefit from this is also a problem of like, why is this the better investment than the other piece of equipment or the other person I could get to work in the laboratory. Those are part of it. I also have to say, in my experience as a community, metrologists tend to be conservative and want to build consensus before we build towards adoption. And we're not at that level of comfort with where we're going with digitalization.
Thank you. Yeah,
If I may.
number 2, yeah.
Thank you very much.
Mark, you butt in, no, jump in if you want to.
Yeah, well, I don't think I have much to add, but I think I also think, first of all, for metrology, I think we are still asking ourselves the question, what's in it for us, in this whole digital transformation thing. And I think we are still searching a bit. Maybe the DCC is somehow the most obvious thing, where we think we can create some value. But there, and I think there's some activity there, which I don't think we are really holding back. PTB was mentioned. I mean, they took a bit the lead there. So, but beyond that, I think it's a bit, yeah, there's so many open questions, how can we as metrology support the digital transformation? And then it's obviously also always a question of the resources. I mean, I can see that here at Metas, there is to get people who would, let's say, transfer what I showed here, but what we realized for my lab, maybe to other labs, because the software components are there. But just to do that, it just requires resources which the other labs don't have, just like that. So they would have to be made available in addition.
Thank you, Marco. Okay, we've got another question.
Thank you very much. My name is Christian Müller-Scholl from Mettler Toledo, and I'm also an accreditation assessor for calibration labs. This might be a little bit different and rather practical question or comment. I'm very happy for Chuck's contribution, which made us aware that metrological traceability has a time dimension. And I think this is exactly what ISO 17025 means when it mentions we need to establish and maintain traceability. And this is, I think, a perfect match. And in my understanding, this says that when I calibrate something on day 0, the values and the uncertainties, the errors and the uncertainties will not be the same at day 1 and day 2, if you agree. So we need to take this into account. And then what I hear very often regarding the digital calibration certificate makes me suspicious, because people think they can build up a traceability chain by just throwing an anchor to the previous DCC on day 3, and the DCC was made at day 0. And that is then, I think, a big mistake and a huge misconception about the about traceability and the capabilities of the DCC. And whoever hears this misconception and agrees to my conception, please warn those guys, this is not correct, this is not true, because it doesn't take into account the behavior of the instrument within its period of use after the day 0 calibration. Thank you.
Thank you for that point. Who would like to respond?
Is that okay? Yeah. So absolutely agree, Christian. When something is reported and given to the next stage in the traceability chain, they need to describe the model of their sub-process. So that's what I showed. And if something is drifting, it seems to be what you're alluding to, for example, because there would also be other environmental effects and how the measurement is actually performed. So really, everywhere, every stage in the traceability chain where a process is going on, it needs a model. And the terms in the model then become components of uncertainty And so you should be satisfied, I think, by such a process. But you're quite right. You can't just take the result and say this passes straight through like it's transparent.
Yeah, thanks, Christian. Yeah, thank you also for your comment. And yeah, I agree. This also gets to the harmonization question. I think with the model, I think, somehow building that in to the process. I mean, I think that timeline could easily incorporate what the model is at each step. But but I think that what Christian just said is important. And if a timeline were to accompany the certificate, then it would accomplish what you're saying. And thank you for presenting that from the accreditor's point of view, because to me that's important.
Accreditors are not yet aware. I am.
Yeah, you are.
So if I can make a comment, we often think of calibration as a statement of what happened in the past. We prepared the sample, we made these measurements, these are the results we got, and there's your calibration certificate. But really, calibration is really about predicting how that artifact is going to behave in the future. Its life is in the future. And so this forward-looking approach, which I think is what you're sort of, Christian, is what you're hinting at, is very important to have that mindset. I think that's the issue of whether you can do that with digital certificates, or I'm pretty sure you can't do it with the regular certificates, paper certificates. They can't look to the future at all. They can't even tell the time. But having that mindset, I think, is very important. Thank you very much. Malcolm.
Malcolm McEwen, NRC. I'm struggling with some of these concepts, and then we're sort of talking about putting them into certificates and having, Marco was talking about the end user can work out what they need. And I'm not sure our end users even know the concepts in the first place. And I guess IMEKO is good because we have this TC1 in terms of education, and we're still talking in the NMI community, and we haven't worked out what it looks like, but I don't think even my end users would understand if I started talking about models for their uncertainties or their traceability chains. We're only just getting our end users in publications to even talk about type A and type B uncertainties and put a real uncertainty budget in. So we've got this disparate end user community, which often the NMIs are directly linking with. There's an education bit that we clearly need to start. Maybe we can start working on that first while we work out what we need at the NMI level. So that wasn't a very good question, but hopefully somebody can respond.
So it was a good question, or a good comment anyway. Part of the answer to your question about unsophisticated end users or people lower down the chain is that the instrumentation becomes more sophisticated, can become more sophisticated. So in the example of the light meter, if it were to receive digital information about its calibration state, then a button could be used to say I'm surveying differences or I'm making an absolute measurement. And so Marco pointed out that there's a instrument manufacturer of VNAs who have now incorporated their software, right? But it's presented to the user in perhaps a slightly less complicated way, so that the typical user would get benefit from it. So part of this, I think, is not to imagine that we need PhDs at the end of the traceability chain, but digitalization will allow us to encapsulate services and deliver them, so that we may be able to deliver traceability information in a useful way through digital. But education is another interesting thing for, along the way.
Okay, we're heading towards the end of our 2-hour slot. I want to check if ND online would like to make a comment or ask a question.
There's one.
Okay, we've got one taker. Mike Brown from Fluka. Can I ask you to make your question?
Yes, I just wanted to comment on the prior discussion here about feasibility, implementation, widespread adoption, and I think it's critical in the same way that solutions for accreditation came about, that solutions for quality management came about. It's really, these things need to be defined, understood, and have some requirements set so that, readily available solutions could be made available to laboratories in industry that abstract these concepts out for them, and they can holistically comply without necessarily being aware that they are. But to get that value proposition understood and consumed is kind of the gray area that we are in now, where we have these discussions about digitalization. We have a good understanding of what we mean. When we discuss this in industry, there's still a large portion that believe digital calibration certificates means a PDF. And until we get over that, plus all of these other concepts and the practical application of them, we're in the requirements and definition phase here rather than execution and adoption.
Brilliant. Thank you very much, Mike. Anybody else online? Would anybody want to make a quick respond at all to Mike's comments before we close? Okay. Thank you. It's my duty then to thank all the speakers, to thank all the discussants, to thank you everybody attention here in Hamburg and also online. So thank you very much for a very successful session. The session will resume again at 10:30. Thank you very much.
Thank you.